Hey guys, welcome to Civil Engineer Sada. So today I'm going to uh, teach you about the prop cantilever. I'm just going to brief you about the prop cantilever and carry out the analysis in Ansys to validate the results. Okay, so you all know what is a prop cantilever. So let me zoom in a bit and let me take a pen here. Okay, so what a prop cantilever. So a prop cantilever is a structure with 1 degree of static indeterminacy. So which means that you will be having if the beam is having only vertical loads. Okay, if the beam is having only vertical loads, then 3 reactions and 2 equations of static equilibrium exist. So 3 reactions and 2 equations of static equilibrium, so the static indeterminacy is 1. So the prop cantilever is a structure of 1 degree of static indeterminacy. So well, again, you can just see here there's a prop here. We call this part as a prop, so we call it as a prop here. Okay, this is a prop, and here it's a fixed edge here, it's a fixed condition here. So you will be getting 2 reactions. One is a vertical reaction and the moment here if no horizontal load exists. Okay, fine. So what one note you have to make is that for the prop cantilever, the vertical deflection at the prop will be 0. The vertical deflection at the prop will be 0, which means that your the profile of bending of the beam will be in this way. Almost means here there will be no deflection, at this part, so there will be no vertical deflection. Okay, so this is what the meaning of the prop cantilever providing the prop there. One extra condition we will get, so we use the compatibility condition to get the redundant reaction. So redundant reaction in the sense the indeterminate reaction, we find it by using this method. So we can analyze the prop cantilever using the principle of superposition and moment area method depending on your conveniency. Moment area method and principal superposition method, this is manually. So by software I will just validate the results. Okay, the downward deflection due to the given load and upward deflection due to the prop must be equal. So that is very important. The downward deflection due to the given load and the upward deflection due to the prop should just hold the load. Okay, so that is the meaning of prop there. So just see the deflection criteria here actually. So this is for a no prop, this is no prop condition, or just a no prop. But here is a condition with prop. Okay, with prop. So with prop, so this is a with prop condition. So you can just see that the prop is giving you a deflection. So the delta 1 without prop and with prop should be equal to 0, which means that delta 1 should be delta 1 here, and the delta 2 should be minus delta 1. So that will equal to 0. Both will get cancelled and it will get as 0. So let me erase here. Yeah, fine. So manually while solving, what we do is we find it by using the moment area theorem, which is as given here. We use the moment area theorem to find the deflection values, slopes, deflections, and even we find the reactions. If we get the reactions, then only we get the deflections, and then we'll go for the BMD and SFD, that is bending moment and shear force diagram. So this is a very simple prop that I'm going to start here. Just see here, analyze the prop cantilever shown in the figure and obtain the bending moment diagram and shear force diagram. So when you obtain the shear force and bending moment diagram, you need to just calculate the reactions first. RA and RB is the reactions that I have taken. Since there is no horizontal load, we can neglect this part of load here. We can neglect it. So just erase that, not required. Now the net deflection at B is 0. That is what the meaning of prop, providing an extra condition for calculating net deflection at B is 0. So we using the second moment area theorem, A1 x1 plus A2 x2. X1 and x2 are the distances of this bending moment diagrams. So I just don't want to show you all the calculations here, just want to concentrate on the SFD and BMD. So that is what we can get from the Ansys software. So I'm just concentrating on SFD and BMD. So this is a prop here, so this is a beam. So just see the SFD, it is 5 WL by 8. It's a general condition of loading, 5 WL by 8. So W is not have any load value, 5 WL by 8, and this is minus 3 WL by 8. So the reaction at B is 3 WL by 8, 5 WL by 8, and the bending moment diagram. Just see the shape of the bending moment diagram here. So what we'll do, we will validate this graph, these diagrams. We will validate. Okay, will validate the graphs here. Okay, we will validate. So this. So get the maximum bending moment. So the maximum bending moment value is 9 WL square by 128. This is the is 9 WL square, 9 WL square by 128. 128. So let's start in Ansys. Okay. So guys, I have opened the Ansys Spaceclaim here. So let's start. Okay, so I just want the XY plane here. So just go to XY here and just click on this point and just get the XY plane here. Okay, dear friends. So select the beam option here. Select the beam line option. From origin, just drag. See here, you in this example, you have not given the value of L. There is no value of L, so I just consider my L value as 5 meter and then solve. Okay, so let me open here. So this is 5 meter here, so 5000 mm. Okay, yes, fine. So just hit here, escape, finish line. So this is a line of 5 meter length. So you can just see here 5000 mm. So what I'm going to do is I'm just going to insert I'm select the line here and just say as prepare profiles and rectangular profile. Just choose a rectangular profile. After choosing rectangular profile, you just need to select a rectangle, one click. So your model is selected here. So one click here, edit beam. So you just see here by default the breadth and height of the beam will be 10 mm into 10 mm. That doesn't matter actually, but still what I'm going to do is I'm just going to change it for my convenience. Let me make it as 100 mm. So here also let me make it as 100 mm. So after that, let us see that is a square section here. So just hit escape, just come to the structure tree and just come back to the design here. Okay, so your prop cantilever with a rectangular cross section and a length of 5000 mm is ready. So let's load our mechanical software. So let's load our mechanical APDL. So this will take time. So let me resume when it opens. Okay, guys, the mechanical APDL has been loaded. So what I'm going to do, see, I'm just having beam of 5 meter length. So let me right click here, view front. So this will give you exactly the front view and it will be easy for you to create the fixed supports. So let's go to the mesh first. So let's go for the default. Let's take it as some 20 mm. So it will be fine if it is the 20 mm here. Update or generate mesh. So the first time will be generate mesh. So the mesh has been generated, my dear friends. The mesh has been generated. So now what I'm going to do, the next thing is you need to apply a fixed support at one end here. So just select here the vertex point here. So automatically it will show you the way here. So the fixed support is kept here, the fixed support is done, and here you need a prop. You need a prop here. Just see, you need a prop here. So this prop should only allow the moment in X direction. No Y and Z direction moment should be allowed. Okay, so let me go back here. So attach, so insert, let's remote displacement. Okay, so let us put displacement here. So where we shall we put it? We shall put it in the other end here. So apply. Now we have to fix the ends here. So let me see here. I don't want the moment in y and z direction. I don't want the moment in y and z direction. So let me make sorry, not y. Yeah, y and z direction, sorry. So make it constant here, constant. Okay, so the x component is free to move, the beam is free to move in this direction. Since there is a roller support here, you can just see the roller support here. Okay, so fine, the supports have been attached. Now we shall apply a force here. So take the edge support here, consider edge support, click on this and hit the geometry, apply to the geometry. Now vector components, yes, now we have to apply the load here, my dear friends. So we will apply 50 kilonewton, so minus 50 kilonewton, so it's in newton, so we have to enter 4 zeros. So this beam has been applied, distributed load of 50,000 newton. Okay, now we come back to the solution part. So let's solve this. So it will take some time. So since it is taking some time, let's go back to our manually solve the propped cantilever. Okay, you need to just see that we need to validate this result, and we should get the bending shear force diagram in this way and the bending moment diagram in this way, in this shape actually, because we cannot predict that it should, since it's a general case of loading, we have to predict it in this way only. So solution has been done here. So insert deformation, total deformation, and what I'm going to do, one more thing is probe the moment reaction. One more very important thing is the beam results, my dear friends, beam results, that is the shear diagram. So it's asking about the path. It is showing me that you have not selected the path here, so I have to select the path. For that, go to model, right click, insert, construction geometry, path. There, after selecting path, you need to select path type, means which what is the type of path you are going to select, like whether you are going to select the 2 points, whether you are going to select the edge. So I'm going to select the edge. So when you just bring it across the edge here, it will automatically select. You just need to click here and just select. So this is the path that we have already created. So now the total shear force bending moment diagram, just select the path here. Yes, perfect. So that has been done. So let us say evaluate our results. So it has given the warning, no problem in that. Yes, my dear friends, just see the profile that we have got. Just see the profile we have got here, and this is the total shear bending moment diagram. So my dear friends, just see here, total shear force. This is 0 at 0 mm and at 3.12 meters. At 3.12 meters, we are having the minimum shear force. Okay, so at this point, the bending moment will be maximum. At this point, our bending moment will be maximum. Okay, so at supports also the bending moment will be maximum, that is 3.124 into e raised to 7 at 0 mm. So let's see here, just see, it is perfectly correct. So you can just see that WL square by 8. So the bending moment at support is higher, then when it goes to the middle, it is becoming a little bit smaller here. So just see the results here. So this is a total displacement, don't worry about this. So this is the diagram here. So total shear moment diagram, total bending moment diagram. Okay, so total deformation here. So we have to see these values, we have to put the values and check there. So again insert, so let's probe the moment reaction at fixed support. So total moment reaction at fixed support, and let's again probe the values of moment reaction at the displacement end. And one more thing what we will insert is we will probe the force reaction. Okay, force reaction at fixed support. Okay, so we will say again evaluate all results. So we have got the results here. So this is the total deformation. So you can just see, my dear friends, so this point the prop cantilever is holding back this subbeam, and here at least it is fixed. So the stresses are very less here. The total deformation is very less, almost zero. See, this is the zero deformation. The blue color indicates zero deformation. So only solving from the software is not the important key one. As an engineer, you have to validate your practical application or your theoretical application, whether my software is giving me correct results or no. So just see this. Here the fixed support is there, hence our deflection is zero. Here also it is zero. Only in the place of, it is not exactly middle also where the maximum deflection is occurring. The middle deflection occurs, the maximum deflection occurs at the center part here, not the center part, little more than the center part when you just go from here. Okay, so in this way, this is the total shear moment diagram here. So you can just see here maximum shear force and the moment reaction. So let's see the moment reaction here. The moment reaction, these are the maximum value over the time. So it is time dependent here. Actually it is a time dependent process here. Moment reaction to, okay, force reaction. So just see the force reaction here. So same, it is 31.248 newtons, kilonewtons. Okay, 31.248 kilonewtons here. And one more force reaction we will calculate here. Beam results, wait, probe force reaction at displacement end. We will calculate it in displacement end here. So after calculating displacement end, see, at the displacement at the propped cantilever region, the, so let's say display we will just result just to show you the probe values. Okay, I think, where is it, probe results. So just need to say the probe results here. So it's off here, it's okay. So the maximum value over the time. So for this support here, if I say the support B is carrying 18.752 kilonewtons of load, whereas my support A is carrying 31.248 newtons of load here. So you can just see that here support A is carrying more load than when compared to support B. Okay, so this is the way you can analyze a prop cantilever in the Ansys software workbench. So let me see again something if I can do with the other results here. So axial force not required, actually the shear force. So we'll just see the total shear force. So just see the total shear force is, the shear force is maximum at this end. Just see, the shear force is maximum at the end A. Here also it is saying that the shear force will be maximum, that is 5WL by 8. If I put my load value as 5 into 50, okay, into L, the length, by 8, then I'm going to get the shear force is maximum here. So this is the correct value that we have got from the software. Shear force is maximum. So let me play here, you will understand. So same thing. Then one more thing, total moment. Let me also do the total moment here. So probe and also beam results, total, sorry, shear force, torsional bending moment. Okay, already I think it is done, bending moment, no. So let's put that value here, bending moment. So let's solve that. Okay, fine. So the bending moment, so the minimum bending moment that occurs, it occurs at this region and at this region here. So the minimum bending moment is occurs on the beam. Okay, so just see here, the minimum bending moment is occurring at this region, that is some part away from the support A. So that is the same thing that we can validate. See here, at this point, so the bending moment, it will change its profile from the sagging to hogging. Sorry sir, yeah, in this way, means it from negative to positive. So from negative to positive, it is changing its sign, or it is crossing this line. So when it crosses this line, the bending moment is 0 here. So the bending moment will be 0. That is what we got from the software. That is what we got from the software, that at this portion the moment will be 0. So that is what we got, and here it will be 0 at the end. Here at the end point here also it is 0, and at this point also it is 0. So I hope you understood how to analyze, or just got the get the information. So front view. So meet you in my next videos. Please, if you like the video, please like my video, share it to your friends, and spread the knowledge to others. So meet you in my next videos. Till then, take care. Bye.